The discovery of 3I/Atlas in early July 2025 immediately captured the attention of astronomers around the world, not only because it was a new celestial object entering our observational field, but because its trajectory instantly hinted that it was something extraordinary. Traveling at an astonishing speed of approximately 220,000 kilometers per hour, about 137,000 miles per hour, the object was racing through space far faster than typical long-period comets from the Oort cloud. Its orbit was not elliptical or closed like those of objects bound by the sun's gravity. Instead, it followed a rare open-ended hyperbolic path, meaning it was merely passing through our solar system rather than belonging to it. Within days, astronomers agreed that they were witnessing only the third confirmed interstellar object ever detected near Earth, following Oumuamua in 2017 and Comet 2I/Borisov in 2019. In recognition of this, it was officially named 3I/Atlas, 3I marking it as the third interstellar visitor, and Atlas, acknowledging the asteroid terrestrial impact last alert system responsible for spotting it. Atlas, designed primarily to detect potentially hazardous near-Earth objects, had once again proven its value not by identifying a threat, but by revealing a cosmic traveler from beyond our solar neighborhood. Despite its dramatic entrance into the scientific spotlight, NASA quickly reassured the public that 3I/Atlas posed absolutely no risk to Earth. Its closest approach would be roughly 270 million kilometers, or about 168 million miles, far greater than the distance between Earth and the Sun. It would not come anywhere near intersecting Earth's orbit, and no scenario existed in which the object could be perturbed into a dangerous path. The comet would reach its perihelion, its closest point to the Sun, by late October, approaching to within about 210 million kilometers, just inside the orbit of Mars. Though distant, this proximity to the Sun promised a period of heightened activity as solar radiation began to heat the comet's surface, releasing gases and dust that could reveal clues about its composition, structure, and origin. Knowing that the comet would slip out of Earth's view for much of October due to its orbital geometry, astronomers rushed to collect as much data as possible before it faded behind the Sun. The earliest observations confirmed that 3I/Atlas was unmistakably cometary rather than asteroid-like. Images captured from ground-based telescopes and early space-based observations showed a reddish halo enveloping the nucleus, a coma that signified active outgassing. This reddish glow intrigued scientists because it suggested that the dust surrounding the comet was rich in silicate minerals coated or mixed with complex organic compounds. As the comet traveled closer to the Sun, its coma expanded significantly, hinting at substantial volatile material sublimating from its surface. What captivated researchers even more was the realization that the comet had been active even before its official discovery. By reanalyzing pre-discovery data, scientists found that the object had been exhibiting signs of sublimation driven by volatile ices other than water, a characteristic highly unusual for most comets observed inside our solar system. Water ice typically begins to sublimate at distances closer to the Sun, but 3I/Atlas appeared to be releasing gases even at much colder, more remote regions of space. Follow-up spectroscopic analysis revealed a fascinating mixture of chemical signatures. There were clear traces of water vapor, which was expected as the comet warmed, but researchers were astonished by the intensity of carbon dioxide emissions. These CO2 jets extended nearly 350,000 kilometers into space, forming one of the most massive gaseous structures ever recorded around a comet. Such vigorous CO2 activity suggested an internal composition shaped by environmental conditions distinct from those in our solar system. Additional spectroscopic markers revealed the presence of cyanide, CN compounds, often seen in comets, but still scientifically valuable, and even traces of nickel, an element not commonly detected in significant quantities in cometary tails. These chemicals offered hints at the conditions under which 3I/Atlas formed billions of years ago. The structure of the coma and tail only deepened the mystery. Instead of a classic, elongated gas tail prominently streaming away from the Sun, initial images showed a coma that extended toward the Sun, an unusual configuration suggesting a plume of dust lifted directly from the sunlit surface of the nucleus. This atypical orientation could be due to the geometry of the comet's rotation or the dominance of heavy dust grain release rather than light gas emission. Later, more sensitive observations revealed a faint, wide tail stretching normally away from the sun, as expected from traditional comet dynamics. However, the tail's position behind the nucleus from Earth's viewpoint made it difficult to detect with standard instruments. The dual structure, the forward-facing dust plume and the faint rearward gas tail, painted a complex picture of how interstellar comets may behave when warmed by a star after drifting for eons through cold, empty interstellar space. Initially, based on the brightness and intensity of the coma, astronomers estimated the nucleus of 3I/Atlas to be quite large, possibly between 10 and 20 kilometers in diameter. Such a size would make it comparable to some of the most massive comets ever recorded. But these early measurements were quickly challenged when the Hubble Space Telescope captured high-resolution images that allowed for more accurate modeling. Hubble's data suggested a much smaller nucleus, perhaps only 0.32 to 5.6 kilometers across. This wide range demonstrated just how difficult it is to measure an object obscured by a reflective coma, particularly one with highly active sublimation. The dust and gas surrounding the nucleus may have been so bright and dense that it artificially inflated early size estimates. Yet even the smaller size estimates did not diminish scientific excitement. The object's high activity relative to its size hinted that its surface was unusually rich in volatile materials. Studying interstellar objects like 3I/Atlas offers a rare and invaluable opportunity for understanding the formation and evolution of planetary systems beyond our own. Each interstellar visitor carries with it the history of its birthplace, chemical fingerprints, structural clues, and isotopic signatures that may differ from anything found in the solar system. Because these objects were formed around distant stars and then ejected into interstellar space, they essentially act as time capsules from the earliest eras of planetary formation. Researchers believe that 3I/Atlas may have originated in the direction of the Sagittarius constellation, pointing toward the dense and ancient heart of the Milky Way. Chemical models and trajectory analyses suggest the comet likely formed around 7 billion years ago, making it significantly older than our own solar system. It probably originated within the galaxy's thick disk, a population of stars and planetary material that predates the thin disk where our sun resides. This means the building blocks of 3I/Atlas were shaped under conditions far different from those that influenced the formation of planets here. Whatever event ejected the comet from its home system remains unknown. It could have been gravitational instability caused by a nearby giant planet, a close approach from another passing star, or long-term dynamical interactions within a crowded early planetary system. Over billions of years, the comet drifted through the emptiness of interstellar space, occasionally nudged by the gravity of massive stars or molecular clouds, slowly reshaping its trajectory until it finally crossed paths with our solar system. This long and complex journey makes it nearly impossible to determine the exact star it once orbited, but its composition offers vital clues. The detection of abundant CO2, organic-rich dust, cyanide compounds, and traces of metallic elements suggests that its parent system may have undergone chemical processes quite different from those in our early solar nebula. For scientists interested in comparative planetology and astrobiology, these differences are crucial. They reveal not just what interstellar objects are made of, but how diverse planetary systems across the galaxy might be. As 3I/Atlas continues its hyperbolic escape from the sun, it will eventually fade back into the depths of interstellar space, unlikely ever to return. Yet the observations made during its brief visit will remain a treasure trove for decades. Every interstellar object adds a new chapter to our understanding of the galaxy's history, and 3I/Atlas, with its intense activity, unusual chemical signatures, and ancient origins, provides one of the richest datasets yet. Its journey through our neighborhood is a reminder that our solar system is not isolated. It is part of a vast galactic ecosystem where materials constantly migrate, offering glimpses into worlds we may never reach, but can study through these rare cosmic messengers.